right, welcome back. What we're going to do is we're going to go through some problems and try to find the limits graphically in this section of tutorials. And we're going to use the definition, or the alternate formal definition of a limit. And this is a very, very important definition that I believe if you understand and you go through and when you find limits, you use this alternate definition. There's so much power that it can tell you how to find a limit and what the limit is. But the key thing is that when you're finding a limit graphically or algebraically or numerically, that when you find it, the right side of the limit, and the right side of the limit, you know this because it has the plus sign, all right, right side. The right side of a limit of f of x as x approaches c needs to equal the left side. And the left side, right here, is with that negative. That's the left side of the limit. And that has to equal L. And if both those right and left side equal the same value, then you know the limit at x approaches c. And this is what we call a two-sided limit. This is what we refer to as both these are one-sided limits. One-sided limits. Okay. But when these two one-sided limits agree from the right and left side, then the two-sided limit, or as x approaches c of x, that will equal L. So let's take an example right here. Let's find, using this graph of this function f of x, as x approaches 0 for this one, we first identify, okay, what is the limit as x approaches 0 in this case from the right side? Well, we take our graph and we can look and start plugging in values, and as we go along this graph, and we approach 0, now realize that we are going, approaching, and plugging in x values getting closer to 0, because that's our input. We're looking at what is our output. What is our output? What is our dependent variable approaching? And it appears that as we get closer to here, it appears to be approaching 0. Now, it's not actually 0, but it looks like it's going to 0. If you see this, we get here, it appears to be going to 0. In the same way, if we take the limit as x approaches 0 to the left of the function of this right here, we can see this, and we are approaching right here and plugging in values, getting closer to here, and it appears that it is also approaching 0. Well, both the right and left values approach the same value, and since they approach the same value, we know that our limit itself for the two-sided limit will also equal 0. That's my donut. It is 0 right there. All right, well, let's try another one. In this one, we are also going to be using the alternate definition of a limit. Find this. Let's find out if the limit as x approaches 1. So this is my input, and we're looking for where is this look like it's approaching. Now, remember, these are the values that it appears the intended heights. Okay, what is it becoming arbitrarily close to? What is that value? Well, as we approach 1, we're plugging in values close to 1, and we can see right here, it appears as I plug in these values, it is going to 2. So from the left side, this would be the limit, as x approaches 1 to the left, with the minus, as it means left. Again, it's left. All right, of this function f of x, it appears to be going to 2. The right side we can look at, and we start plugging in values close to 1, and as we do that, right here, and it appears as we go in these values and plug them in, that is going to 2 as well. So the limit as x approaches 1 to the right side of the function, that means to the right again, okay, that is going to also appears to be approaching 2. So the outputs, and you're looking at this by looking at right here. What is the outputs approaching? Now notice that there is an open circle here, and this is where students sometimes get a little confused. The open circle, remember, limit is the intended height. And it appears that it is going to this value 2 to the left, and this value right here 2 to the right. Okay? The intended height is 2. Because the left and right side both approach 2, that means that the limit as x approaches 1, the two-sided limit, will equal 2. And it does exist. Now the question is, what is f of 1? So this is an expansion question. Does that exist? Well, 1, we're actually looking for what is the value at x equaling 1. Well, the value, when we input 1, is actually this closed circle right here. The actual, oops, not right there. Yeah, the actual value of 1, I apologize. The actual value of 1 appears to be -1. Notice how the limit and the actual value are different. Well, because that they're different, that's okay. Limits are the intended height. Sometimes functions have intended heights, or values that they appear to be approaching, but their actual values are kind of outside what it's approaching and are something different. And this happens to be the case. The limit is 2, but the actual value is -1. All right, well, let's try one more for graphing. All right, and using our definition, alternate definition again. All right, find the limit if it exists, if the limit as f(x) approaches 1. Well, as we approach 1, let's go through here. So let's find our limit. The limit as x approaches 1, we'll go from the right first. It doesn't matter which order you do it, just that you do both sides. And you check both sides. Well, as we go here, I'm approaching +1. And as we approach +1, right here, it appears, here's 1 right there, it appears to be going to 5. Appears to be going to 5. Okay, or actually -5. If we take the limit as x goes to 1 to the left side of the function, as we go here, once again, it appears that once again that is going to -5. So they're approaching the same value, 5 and 5. Okay, and we can find that. All right, we can also graph it, look on the graph itself. All right, here is that 1. As we get closer to 1, it is going to that 5 value. All right, so we are going to -5, and it does exist because that's the value it's approaching. Find if it exists at f of 1. Well, f of 1, what is f of 1? Well, f of 1 is the actual value. Well, that actual value happens to be -5 as well. So when we have a limit and the function, when they equal each other, all right, that is actually what we call the definition of continuity, all right, or where a function is continuous. It's continuous when the limit, as x approaches c of a function, equals f of c. In this case, the limit actually equals the value of the function right here, so we would say it is continuous. All right, f of x is continuous at x equaling 1. Whereas in the other example right here, this is not continuous. There's a hole, we call a hole. And this is actually discontinuous. It is discontinuous at, all right, at x equaling 1, because the limit as x approaches c of the function does not equal f of c. They're not two in the same. So we just actually went through graphically what limits are, and we kind of showed the application of how it talks about graphs, and that it can help us prove discontinuity, all right, discontinuity, and also continuity, or where a function is continuous, by saying that the limit equals the actual value of the function. All right, so those are 2 or 3 different examples of how we can use limits or find limits graphically using the alternate formal definition of a limit. All right, hopefully that helps, and enjoy your day.